Hello everyone, and welcome to Calculus BC. In today's episode, we're going to be discussing Chapter 9.6, which is Absolute versus Conditional Convergence. And so this actually stems off of being one of the consequences of having learned the alternating series test for convergence that we saw in the last episode, where what we did was we began with the alternating harmonic series, right? So we saw that as the summation from n equals 1 to infinity of negative 1 to the n plus 1 over n. And what we saw was that when we were able to establish that a sub n was decreasing, and we were to say that the limit as n goes to infinity of the actual sequence itself, right? Not the piece with the alternator, but just the actual sequence itself, the absolute value of it. Once we saw that those terms went to zero, the fact that the alternating system exists meant that by the alternating series test, we could say that the limit as n went from, not the limit, but the summation from n equals 1 to infinity of the alternated harmonic series converges. But what we have to do now is we are going to establish that this particular series here doesn't just converge on its own. What we say is that this thing actually converges conditionally. And so this is what we call a conditionally convergent series. And the reason why it's conditionally convergent is because the condition that forces this thing to converge is the alternation. So if I was to look at this a bit of a different way here, if I was to say, okay, let's remove the alternator altogether. If I was to say from n equals 1 to infinity of the absolute value now of negative 1 to the n plus 1 over n. Well, if I absolute valued the entire thing, what I would get would be the summation from n equals 1 to infinity of just the regular harmonic series. And we all know this thing diverges, right? So it's harmonic series, therefore divergent. And again, that can be assumed knowledge at this point. You also could have said P is equal to 1, therefore divergent by P series. Either one would have been fine. But the fact that this thing diverges when absolute valued and yet converges when it's being alternated, what that means is that we are looking for a conditionally, or rather we are looking at a conditionally convergent series. So once again, therefore, conditionally convergent series. And so hopefully that makes a certain degree of sense, that the condition of the alternator is what forces a series to converge in this particular case. So what we're going to be doing today is we're going to be extending this idea into absolute convergence, which is when, hey, if we didn't even have the alternator, would we need it to necessarily converge? You know, would something that is convergent with even with the alternation, would something diverged with the alternation, would that cause the absolute value of it to diverge? So we'll explore that in a few examples here. So give me a second. Let me go and get the next example on the board here, and then eventually we will get into a strict definition of as to what this actually does. So this example that I'm coming up with next here has the sum from n equals 1 to infinity of, looks like, negative 1 to the n plus 1 over 1 plus n squared. So if I wanted to expand him out for just a second here, and not just expand him out, but I'm going to go ahead and just rewrite him. That way the alternator can be seen more clearly. What we're going to do is we're going to check and see, and the prompt for this, and this is where I want to be very clear, the prompt for a problem that looks like this is determine if the series is absolutely convergent, conditionally convergent, or divergent. So that's going to be the prompt of this particular problem here. So that means that I could potentially find myself doing a couple of different series tests on this series here. The first thing I'm going to do here is I'm actually going to go ahead and take the series with the absolute value in place. So that's going to be negative 1 to the n plus 1 over 1 plus n squared. And if I was to take the absolute value of the terms, that would, in a sense, get rid of the alternation here. So I'd have 1 over 1 plus n squared. So I would have totally positive terms. Now, hopefully, the next thing is going to make a little bit of sense. I'm going to go ahead and establish that I'm going to go and let f of x equal 1 over 1 plus x squared. And I'm going to say f prime of x is equal to, actually before I do that, I'm going to call him 1 plus x squared to the negative 1. I think we all see what I'm about to do here, but if you don't, I'm about to initiate the integral test on this thing. And the reason why I'm establishing using the integral test on this one is because, it looks like something that could be integrated, right? I could probably try and do limit comparison on this thing if I really, really wanted to. It's not a huge deal, but we haven't done the integral test in a while, so I'll go ahead and do this. I'm going to say negative 1 plus x squared to the negative 2 times 2x. So that's going to be negative 2x over, looks like 1 plus x squared. So it looks like my critical number here is going to be 0. So I'm going to go plus minus on that one. And so I can say then that f is decreasing for all x greater than or equal to 1. F is continuous and positive. Now again, I chose to use the integral test. We haven't done it in a while, but I will leave it to you. You could have done limit comparison or something like that to see how this thing behaves. No worries there, but we'll go into initiate the integral test here. We'll keep on going here. So from 1 to n, limit as n goes to infinity of looks like 1 over 1 plus x squared dx, which will integrate into tan inverse of x on 1 to n, limit as n goes to infinity. So I've got tan inverse of n minus tan inverse of 1, limit as n goes to infinity. And what I end up getting here is pi over 2 minus pi over 4. And so what I can say here is I can say, therefore, by the integral test, the sum, or the integral from 1 to infinity of 1 over 1 plus x squared dx converges. And therefore, I'll go and just say the summation from n equals 1 to infinity of the absolute valued version. So that would just be 1 over 1 over 1 plus n squared also converges. Now, from here, an additional summary is going to need to be made here. What I've just determined is that the absolute valued version of my series converges, which means, if you remember from the alternating series episode, we determined that when a series alternates, the terms decrease even faster than they normally would. So that means that, hopefully it makes sense that if all the positive terms decrease, right, when they're all being positivized, that means that when you alternate them, they would converge as well. So I can go ahead and sum up all of this and say that because the sum from n equals 1 to infinity of the absolute value of negative 1 to the n plus 1 over 1 plus n squared converges, I can actually conclude that the sum from n equals 1 to infinity of negative 1 to the n plus 1 over 1 plus n squared, we say converges absolutely. And so hopefully that makes enough sense there. Again, we just proved that the totally positive version converges, which means the alternated one would converge, which is absolute convergence because both versions converged. So hopefully that makes sense. I will be back in a second with the next episode. So hopefully that makes sense. I'll be back in a couple seconds with the next example. In this next example here, I'm going to go ahead and determine once again, if this series is going to be absolutely convergent, conditionally convergent, or just simply divergent, right? And so what I'm going to do here is I'm going to go ahead and figure out what this thing does when it's absolute valued. So I'm going to go ahead and just do negative 1 to the n plus 1, n plus 2 over n times n plus 3. In absolute value, I'm going to go ahead and call that the sum from n equals 1 to infinity of n plus 2 over n squared plus 3n. Now, in this particular case here, I want to just draw upon some intuition here. I don't see a u sub at play, so I don't think this is going to be an integral test. But what I can do is I can look at the dominant terms here and know that as my n values get super, super large, what is the end behavior of this thing? And I can go ahead and suspect that this thing is probably going to diverge. But the way I'm going to prove that is I'm going to use our good old buddy, the limit comparison test. Remember that guy? So I'm going to go and compare this to the summation from n equals 1 to infinity of the harmonic series. And so the reason why I compare it to the harmonic series, once again, just to draw back to the comparison test, is because at the end behavior, all I have is n over n squared, which is going to be 1 over n. So I'm going to say compare him to 1 over n, and I'm going to say a harmonic series, therefore divergent. And now I'm going to go and use the limit comparison test on this thing. So I'm going to say the limit as n goes to infinity of n plus 2 over n squared plus 3n. Hopefully it makes enough sense that by dividing by 1 over n, I'm multiplying by its reciprocal. So the limit as n goes to infinity of n squared plus 2n over n squared plus 3n, negligible difference. This guy goes to 1, which is finite and positive, and therefore by limit comparison, the sum from n equals 1 to infinity of our original function, so that's going to be the one in absolute value right there, so that'll be n plus 2 over n times n plus 3 diverges, right? So in other words, right now the absolute valued one diverges, but because this originally came with an alternator, we may want to check and see if the alternated version actually converges. So what I'm going to do is I'm going to go ahead and just take a look at that. So I'm going to say, all right, so we know that the absolute valued version diverges, but let's go ahead and say from n equals 1 to infinity of negative 1 to the n plus 1 times n plus 2 over, I'll go and say n squared plus 3n. Now, because I have an alternating series, I'll probably go ahead and just establish the alternating series test on this thing. I'll go and say then that a sub n decreases, and that the limit as n goes to infinity of n plus 2 over n squared plus 3n goes to 0. So I can say, therefore, by the alternating series test, the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n plus 2 over n squared plus 3n converges. Now, because we diverged when absolute valued, but converged with the alternator, we need to lock those two things in together and say, in summation, the alternated version of this, right, n plus 2 over n squared plus 3n, will converge conditionally. The condition being the fact that it has an alternator conditionally. So hopefully that makes a certain amount of sense. I'll be back in a flash with this absolute versus conditional convergence actually explained. Give me a second. Okay, let's take a look at absolute versus conditional convergence actually explained the definition. So we've been doing a couple of examples here, and I'm hoping that I've been leading your intuition to this idea here, and that is that if the absolute value, right, and this is the first condition here, if the absolute value of the series converges, that means that then the regular version of the series would also converge, right? So, and again, we saw that in the first example. We saw that the one that integrated into inverse tangent, when we absolute valued it, that one definitely diverged with the absolute value, which meant that the regular version of him would diverge, and they call that absolute convergence. If the absolute valued version diverged, but you found that the alternated version converged, we called the series conditionally convergent, and the condition being that the alternator. The alternator forced the convergence on an otherwise divergent series. And then the last one, which kind of reminds me of a line from Rocky IV here, what Drago said about Apollo Creed. If the series diverges, then the series diverges, and hopefully that makes sense. I mean, if you take the alternated version and it diverges, then it makes sense that the absolute valued one would just diverge. So you wouldn't even need to test the absolute valued version. If you just knew you diverged, even though it was alternating, it would just diverge automatically. And so let's take a look at that example, because I haven't done one that was like that yet. But if I was to do, let's say, the summation from n equals 1 to infinity of negative 1 to the n plus 1 of n over n plus 5. Well, actually, this one is a bit odd, right? Like, if I was to do the limit as n goes to infinity of negative 1 to the n plus 1 times n over n plus 5, this thing would actually bounce back and forth between negative and positive 1, right? The alternator would make it go negative positive, and the limit as n went to infinity would make this guy go to 1. So what I could do, actually, is I could split them up into two different limits here and say the limit as n goes to infinity of the negative version of this, and then the limit as n went to infinity of the positive version of this. And since the limits don't agree, all we can say here is that the sum from n equals 1 to infinity of negative 1 to the n plus 1 of n over n plus 5 diverges. And if we had to label a test on this one, this would probably be akin to the divergence test, right? So diverges by divergence test. Now, hopefully it makes sense that when that happens, I don't even need to worry about the absolute valued version of it. And if you can imagine what's going to happen with the absolute, if I put absolute value in here, that would just make the alternator go away. I'd end up with 1 anyway, so that doesn't really do anything. And so hopefully that idea makes sense, that when the alternated version diverges, then there's no need to test the absolute valued version. I think that's actually kind of a good thing. So hopefully this makes enough sense. As always, please leave comments or questions in the comments area. I will see you all in the next episode.